On Tuesday, the 22nd of May 2012, the Climate Change Group welcomed Professor Myles Allen, Professor of Geosystem Science at the University of Oxford, who considered the scientific basis for linking greenhouse emissions to climate change.
I'm Myles Allen. I'm a Professor of Geosystem Science in the University of Oxford, based both in the Department of Physics and the School of Geography and the Environment, and I've been working on the problem of attribution of cause and effect on the climate issue for about 15 or more years now. And most of this work has been around the area of attributing large-scale trends in global temperatures, this kind of question. It's only relatively recently that the question of routine application of cause, addressing the cause and effect question for individual weather events has really come to the fore. We sort of started talking about this back in 2003 in the context of the heat wave that occurred in that year. But it's a slow process building the science and the support for this. This kind of event is even possible. I mean, a couple of things that Silke said, which I want to sort of start from, so to speak, in this presentation. You know, she mentioned the difficulty of establishing cause and effect for a long-term harm resulting from, say, slow sea level rise in a particular region. And she's quite right that the kind of changes that you could attribute directly to climate change are all going to be very slow ones. You know, I would summarize by saying for the foreseeable future, in the lifetime of anybody alive today, it's pretty unlikely that that category of harm is actually going to become significant. All of the interesting harms that we need to worry about are those that relate to the changing risks of extreme weather events. The reason I'm saying that is because even a change happening over 30 years is still, in one sense, a slow weather event because fluctuations in climate happen even on 20, 30-year timescales. And so you're still looking at a, you know, what's the risk of this slow event having occurred even without climate change, and, you know, regardless of essentially what timescale you're looking at. So we are talking about this problem of establishing cause and effect probabilistically. I'll show you a couple of examples of events that we're looking at to give you an idea of the kind of evidence that you might be confronted with if you were to call an expert in to court. For example, and I hit the wrong button straight away. Okay, I'll use that. Okay, so one example, of course, which has been heavily discussed in the literature over the past couple of years, is the 2010 Russian heat wave. You can see in the thermal image in the back there how we had a very localized pattern of very, very high 12-degree temperature anomalies in central Russia, and which caused, again, estimates vary, but some estimates in the tens of thousands of deaths at least, and in the 10 to 20 billion range cost to the Russian economy. The question which sort of confronts us is trying to work out, you know, to what extent human influence on climate might have contributed to the risk of that heat wave. And I'll come back to that, but first talk about a couple of other events rather closer to home. This was the event that sort of got us going on the whole attribution issue. This was Oxford being flooded back in 2003. There's nothing like, you know, climate change in front on your back door. That's not my back door, but it's neighbours actually. In fact, a colleague's house is actually the one we're looking at here. So we all felt pretty strongly about the climate change attribution question at the time, and it got us working on this area. It's interesting that, you know, politicians have come out saying very strongly, you know, John Prescott back in November 2000, people know that something's wrong and that climate change now affects them. That was a statement that set a lot of scientists very uncomfortable at the time because it wasn't a statement that we recognized as one we could support. More recently, Al Gore has started saying, now we're not only rolling 12s, we're rolling 13s and 14s and soon 15s and 16s, the analogy of rolling a dice. And one thing, if you take anything away from this talk, I'd like you to take away the message that that is a very, very, very unhelpful image, even if there's any way in which you could construe it to be true. The reason is, if you roll a 13 with a pair of dice, you've seen something that could not have happened if the dice hadn't been doctored. And that is something that we are not seeing in the weather we are seeing today. That does not mean human influence on climate is not having any impact on extreme weather, but it is, at the moment, you would struggle to find an expert who'd be prepared to say that a weather event has happened which could not have happened in the absence of human influence on climate. And you would certainly find many more experts to stand up against that expert if you were to find such an expert. And therefore, we're working entirely in this game in terms of how much has the dice been loaded. The main reason for this is the uncertainty we face in actually characterizing what the climate would have done if we hadn't interfered with it. That's the big uncertainty in this, is how might the climate have been if we hadn't interfered. And one of the things I'll be showing you is that it's far, far easier to say how much a risk might have changed relatively, say that the risk has gone up by a factor of 2, the risk has gone up by a factor of 3, than it is to say in absolute terms what the risk is. This may sound counterintuitive, but it's very difficult to say, we've seen a 1 in 1,000 year event with great confidence, because that means you have to be very sure what the properties of internal variability in the climate system are on timescales of 1,000 years. That's something we have very, very little information on. But to say that a particular external driver has increased the risk of an event by a factor of 3, that's the kind of experiment we can do. And that's the kind of question we can address with the models we have available today. So, think in terms of relative risk. Don't start worrying about searching for events that could not have happened or, would be, a 1 in a million event without human influence on climate, because then you get stuck on, quantifying those 1 in a million chances, which are very, very hard to do, and you will struggle to find any scientific support for. The key problem is, of course, that Oxfordshire, I showed you a nice picture of flooded Oxfordshire. Oxfordshire has flooded before. The floods we had in 2003, in fact, only came up to the top of that bicycle rail here. So they were pretty severe, but they were dwarfed by the floods we saw on this plaque. You can't read the numbers on this, but there's a nice cast iron plaque in Shillingford which shows that floods were well over people's heads back in 1803 and 1947, and these sort of iconic floods of the past. So how can we attribute, how scientifically can we attribute an external influence to flood risk when we know that these floods happen anyway? What can we do to try and pin down how the risks are changing? This is one experiment that was done recently, published last year, looking at this question of how are external drivers of climate loading the dice towards particular events happening. So the challenge you face in this is that the events that do damage are typically the ones that don't happen very often. Obviously enough, people tend to build houses to deal with the events that they know happen every year. What they don't do is proof their properties against events that they're not expecting, that therefore haven't happened for 50 years or more. So if you're going to understand how, again, back to the dice analogy, you're asking the question, how are the odds of a 666 changing? And to see how the odds of a 666 are changing, in principle, if you want to see that directly, you have to roll lots of 666s to see if you're getting the right number, okay? And, therefore you have to roll the dice many, many, many times, not just enough to see a single 666, but enough to see that you're getting too many of them, okay? And that's the challenge we have. So this is, in some ways, a much harder problem than just trying to sort of pin down a trend in global temperature or something. You've got to actually understand what's happening right out in the tail of the distribution. What we're doing to do this this is the approach we're taking in Oxford, other groups are taking very different approaches, is actually using computing resources donated by the public around the world. So we're actually getting tens of thousands of people to run these simulations for us, because that actually allows us to roll the dice often enough to be able to see what's happening to the risk of these extreme events. And the kind of models we're able to use, even though we're running these on PCs, they are basically the same models that are used for forecasting the weather. We just run them slower than they do in weather forecasting centers, because of course we're not time constrained. We can wait to see what the answers are. But they, it's crucial that the models you're running actually do resolve the kind of weather events that have an impact. These are some of the results that are coming out of these studies, and the very important point to stress is that not all events that do damage are being made more likely. I like this particular juxtaposition. On the left, you see a plot of how risks have changed of a flood, an autumn flood, such as the one that occurred in England and Wales in autumn 2000. So this is a plot which has return time in the horizontal, so less likely events are off to the right, okay, and magnitude in the vertical, so worse events are higher, so higher floods are in the vertical. And you'll see in the blue dots indicate the climate as it was in 2000, and you'll see that, predictably enough, higher events don't happen as often. That's why that line slopes up to the right. And then the green fuzzy area is the way we think the climate might have been if we hadn't raised greenhouse gas levels over the past century. The reason it's fuzzy, of course, is we don't know exactly how the climate would have been. There's a lot of uncertainty to that, but you can see on average, we're looking at something like 100% increase in risk, around a doubling of risk as a result of the greenhouse gas increase, but a lot of uncertainty around that. On the right, so this was addressing the question of how the risk of a flood in the autumn has changed in the UK. But in another follow-up study, Alison Kay and co-workers in Wallingford looked at how spring floods have changed. So in effect, they used the same data to look at how the risk of a flood that didn't happen in the spring of 2001 how the risk of that flood happening or not happening may have changed as a result of human influence on climate. Now, this may sound really arcane to you. This is what are academics doing, worrying about floods that didn't actually happen. But I hope you'd recognize that a flood that doesn't happen has almost the same impact as a flood that does in terms of its, okay, I don't need to hammer that point, I'm sure, to you. Although sort of when I'm talking to the public, it's often sort of puzzles people why we should worry about these things. But the point is, we have had very substantial floods in springtime. The last really big one was in 1947. And those have a very different cause to floods that happen in the autumn. So spring floods happen because we have an accumulation of snow, which melts suddenly when it gets rained on, and then you have massive flooding. Now that's apparently, according to Alison's results, something that has been made less likely by greenhouse-induced warming. Fair enough, we don't have so much snow around in the spring. On average, we don't have so much snow around in the spring. Of course, we will occasionally get snow events still, but we're seeing changes in the type of, and we're seeing a long-term reduction in springtime snow cover in this region. So that shows you a challenge you would face if somebody was claiming to have been affected by flooding. A defendant could then, if you were acting for the plaintiff, a defendant could stand up and say, but what kind of flood? And point out that other kinds of flood might have in fact been made less likely by human influence on climate. And you'd have to unpack whether the net impact on your plaintiff was positive or negative. And it's very important to recognize that, but to avoid the trap of thinking that whenever a bad weather event happens, and if you listen to the media, you would definitely get the impression that whenever any extreme weather event happens, it's something to do with climate change. We've had people blaming sea ice retreat in the Arctic for the snow events we've had this winter. I mean, maybe one day the science will come down onto suggesting that it might play a role, but at the moment, I think most scientists would say, well, we had snow events this winter because that happens sometimes. And, most of the events we're seeing are still, we really couldn't say either way whether human influence on climate has made them more or less likely. So it's important to sort of sort of stay neutral on that question, you know, until the evidence is in, at least, rather than jumping to conclusions. Back to the Russian heatwave example, this illustrates another problem we face. Here's another one of these return time diagrams. I kind of, you know, I make no apology for these diagrams because this is the nature of the evidence we have. We are seeing changes in risk, so that this is the kind of message you would have to communicate to a judge or jury if you were ever actually faced with establishing this kind of question in court. And one of the challenges you face is that what was observed in Russia in 2010 was, you know, a month in which temperatures were 6 degrees on average above normal over a large region. And of those 6 degrees, perhaps only 1 degree or less was the contribution from human influence. So it's looking at this, you know, the big black arrow is the total anomaly which occurred in 2010. And the little red arrow, vertical arrow, is pointing out, you know, only a relatively small part of that was due to human influence, was the contribution from human influence. So you would easily find an expert, me, for example, who would stand up in court and say this was mostly, in terms of its magnitude, this event was mostly natural. Okay. But then if we ask in terms of probabilities, how is the chance of temperatures exceeding the threshold which was observed in 2010, how has that chance changed as a result of the large-scale warming that's occurred since the 1960s, most of which is attributed to human influence? Well, you see that the horizontal red arrow indicates a factor 3 or so increase in risk. If you sort of read off from the bottom scale, you're talking about a 1 in 100-year event going down to a 1 in 30-year event or something like that. So if you think of risk, you know, as apportionable, as Silke was talking about, then you could say that if risks have increased by a factor of 3, then 2/3 of the current risk is attributable to the large-scale warming. So you could then get another expert, possibly the same expert you had before, saying this event was mostly anthropogenic, if you think in terms of probability. At that point, I don't know, your judge might start to feel a little confused. But that's the nature of the evidence. We can't make it simpler than that, because that's what we're talking about. That's what we're talking about happening. The numbers, of course, do matter, and this, of course, is an old quote now, but one which sort of, again, got us going on looking at these, quantifying these numbers from David Grossman's article back in 2003, where he was saying that, you know, maybe you will need to see an increase in risk of around a factor of 2 for tort liability to start to apply. And we have seen events, notably the European heatwave of 2003, where we think that the contribution of human influence may exceed that threshold. There is a debate on, which we might, since this is A4ID, the sort of convening this, I thought I should highlight the fact that there is a debate on about whether this sort of development in attribution science is a good idea, particularly with respect to its potential impact on developing countries. Mike Hume, a colleague who I know well and get on reasonably well with, was very critical of this back in last autumn, basically pointing out that countries such as, you know, African countries without good weather models and access to good weather records might potentially be disadvantaged by this kind of, you know, focus on, you know, trying to quantify harm from human influence on climate. Just to sort of reassure you on that score, if there's concerns on that. I mean, I'm a few more minutes. Yeah. Okay. I just wanted to show you some new results which were coming out again from these sort of studies, looking at a particular region in Africa. We've been looking at the Congo basin region, which of course is of particular interest. It supports Africa's main rainforest, which is sensitive to long-term changes in precipitation. And of course, there have been concerns expressed about the potential stability of the Amazonian rainforest as climate changes, and attention is now turning to the African rainforest and asking how stable they be, how at risk they might be from climate change. So the challenge we have here is this very striking gap in this map of weather observations over Africa. You can see there's absolutely no data coming in from the Congo. And of course, when I commented on this to an expert in weather observations, the obvious answer is, well, you'd have to be a very brave person to go back regularly to monitor a weather station in that part of the world. I mean, sort of sadly, therefore, for several decades now, we've basically had no direct observations of climate there. But what could, is Mike right that, any region like this with poor weather data would automatically be disadvantaged in a debate about attribution of harm to human influence on climate? I'd like to argue that it's not necessarily so that regions like this would be placed at a disadvantage. The reason is that we don't actually need direct observations of what's going on in a region to infer what's going on based on observations of what's happening elsewhere. This is what happens in weather forecasting all the time. You don't have direct observations of the rain band that's coming in unless you happen to have a rain radar pointing straight at it. Generally speaking, you're inferring where it is based on observations of lots of other things that have gone on in the antecedent few days. And this goes on the climate timescale as well. So we can work out what was going on in the Congo, if you like, by sort of looking at the water flowing in and out of that empty box over the map, to work out, how much it was raining in the past. And we can also ask, how has rainfall risk, what's been driving any fluctuations in rainfall risk? And one of the really striking results that came out, this is a comparison in blue of rainfall inferred from observations, as I was describing. And then in black, rainfall we've seen in these hundreds of thousands of model simulations we've been running around the world on people's PCs, simulating what would have happened, what might have happened in the Congo over the past 60 years. And the really striking thing about this plot is just how predictable rainfall is here. You wouldn't see anything like this in the UK. It would just be a big grey band and wiggly lines. Whereas in the Congo, the black line and the blue line go up together very predictably. This is a part of the world where rainfall, monthly rainfall, is apparently highly predictable. And if we look at what's happening to changing drought risks, the green, red, turquoise, and black lines are the sort of 60s to 90s decades. And the dark blue curve is this return time plot for the 2000s, which suggests that the large-scale trends we've seen in climate that have occurred since the 1960s may have enhanced drought risk in the Congo. So if a drought were to occur next year in the Congo and adversely affect the populations that are supported by rain in that region, which is basically everybody, then you could make a case that the large-scale change in climate that we've seen since the 1960s, not all of which is anthropogenic, but we've got a case for saying a big chunk of that is anthropogenic, played a role in the risk of that event occurring. So I don't think this line automatically disadvantages developing countries. It's very important that we address this kind of question, and we are focusing on this, and we're actually hoping to develop a research program specifically targeting Africa, because as scientists we're very conscious of the fact that we don't want to end up only helping rich people. I mean, we need to be we need to be even-handed in this, and it's therefore important for us to do the research to make sure that some parts of the world that may not have been so well served by climate modeling to date are that we keep an eye on them. Indeed, if anybody wants to know more about that, please talk to me afterwards about that initiative. To sort of sum up here, that just sort of goes to show that globally we can do this science, and this there isn't an obvious it doesn't obviously load the deck in terms of one part of the world versus another. But things, takeaway messages for you about things you'll need to think about if you ever get serious about attributing harm to human influence on climate. I don't see in the next decade or two a couple of things changing. One is the evidence will remain probabilistic. It'll remain in the nature of we've loaded the dice in terms of this event happening. In some ways that may be an advantage in the sense that weather events happen. It's over. The damage is done. And therefore, the arguments afterwards are about how different factors may have contributed to the event of that, to the risk of that event occurring, But you won't in that situation need to worry about the statute of limitations issues that Silke was raising, which would definitely be a problem if you're sort of waiting for sea level to rise, for example. I mean, it takes a very long time for that to happen. And you'll also have to contend with this problem of multiple interpretations of the same evidence. You could take the same evidence and make it sound very different by saying it was mostly natural in terms of magnitude or mostly anthropogenic in terms of risk. And both of those statements could be true, but they carry a very different message. So you're going to have to deal with explaining that to people. What I think will change is that we are increasingly goading the weather services into I mean, they're quite willing to get into this game. There's increasing interest in the weather services in developing regular assessments of the contributions of different external drivers to individual weather events on a routine basis. So at the moment, every year, the US National Ocean and Atmospheric Administration releases what they call a State of the Climate Report, which is just an assessment of what happened in the previous year. Temperatures were high in this region, low in that region. So it's just they have almost a statutory duty to avoid saying why in their State of the Climate Report. However, this year, for the first time, in parallel, not as part of the State of the Climate Report, that would be going too far, a preliminary, provisional, lots of caveats around it, attribution assessment will be made. So a series of studies will be gathered together to address questions about why in 2011 we saw the weather we did. And this is sort of testing the water towards the question of whether down the line, this is a collaboration between NOAA and the UK Met Office, I should stress, and down the line with the question, we want to start asking, can we, as a scientific community, support doing this every year? Is the demand for this information? I think there will be demand for this information, but we'll see. We're also interested to see how the information is received, what's done with it, whether it's badly misunderstood, and so we're testing a lot of things in this process. If I might throw in an advertisement, we are holding a workshop on this whole process, a sort of lessons learned from looking at 2011, where do we go now, on the 12th to 14th of September in Oxford. And the second day of that workshop, that's the Thursday, which I think is the 13th, is open. We're really interested in getting people who might be interested in this kind of evidence to attend, so not just scientists. I mean, so we want to know what are the questions people actually need us to address, because as scientists, we can do this kind of work, but we're conscious of the fact that the questions we may be addressing may not be the ones that people actually want answered. So we're throwing the second day of that workshop open to the broader community, and we're hoping to get good participation from a broad range of people. Obviously, there's a lot of interest from the insurance industry in this, on water planners and so on. So they're always signing up. But we'd like to see some representation from this community as well, because this is the way the science is moving. And as this kind of information becomes available on a routine annual basis, I think it will have quite a profound impact on your ability to make causation claims stick. So talk to me afterwards if you want more details of that meeting.
Great. Thank you very much. Thank you.